Next, we're going to look at conditional statements. It'd be a statement like, if, then. You have a hypothesis and a conclusion. If this is true, then this is true. And let's take a look at some examples. If you work 8 hours, then you will receive full pay. So again, you have maybe like your P would be you work 8 hours. Q would be you receive full pay. So a lot of authors, I think she uses this as in terms of a promise. And that's kind of a good way to deal with this if-then statement, with these conditional statements. And I think that's a way to understand it well. So let's go through this and see if we can understand it, thinking of it as she does in terms of a promise. So again, P implies Q. We have true, 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 false, false, true, false, false. And so let's think of this again. You could think of this particular example. If you work 8 hours, then you will receive full pay. That's kind of a promise. So is this, in this first case here, is this promise kept? And the answer is yes, because you worked 8 hours and you received full pay. So that's true. So again, you could say promise kept. But suppose you worked 8 hours, but did not receive full pay. So you could say false, because the promise was broken. You worked the 8 hours and you received full pay. Now, how about this case here? When you don't work the full hours, the 8 hours, yet you receive full pay. What would we say about that statement this time? And this one is a little bit harder to grasp, because you received the full pay even though you didn't work the 8 hours. So usually they say, well, even though you got the pay, even though you didn't work the 8 hours, no promises were broken, because you really didn't even fulfill your part of it, but you received full pay anyway. So you can't say that any promises were broken. You were kind of given, you might say, extra grace. So in that case, that's considered true, because promise was not broken. And now in this final case here, you didn't work the 8 hours, and therefore you didn't receive full pay. That seems pretty logical. And for sure, that one is going to be true because you didn't fulfill your part. So no one was obligated to give you the full pay. So once again, you might say promise not broken. So you're really evaluating if the promise was broken, it's going to be false. If the promise was kept or not broken, it's going to be true. These all kind of make logical sense, except often this is the one that kind of trips people up. If your hypothesis is false, but your conclusion's true, that's considered true. So this is the truth table for the conditional statement. Now you have a biconditional statement, if and only if. P, if, and only if Q. So, and this is often written like this. And this comes up in math a lot. And so let's take a look at this. And once again, let's look at an example. You will be given a car. If and only if you get a job. So again, you might want to say, okay, let's write this differently. This means if you are given a if you are given a car, then you got a job. And if you got a job, then you are given a car. So, and what's the truth table for this? Once again, we'll keep that promise idea in mind. And once again, if you want to do the PQ thing, you P is you are given a car. Q is you get a job. And once again, we make a truth table. We'll think of the promises kept idea. and promises not broken. So now, if you're given a car and you got a job, then the promises were kept. You know, you got a job, therefore you got a car, therefore you got a job, you got a job, therefore you got a car. This one is going to be true. This one here, you were given a car, but you did not get a job. So that's going to be false because the promise was broken. This one, you got a job, but you were not given a car. Again, remember, it's supposed to go both ways. It's a two-way street. This one is false because the promise was broken. You got a job, but you didn't get the car. And so in this one here, you're not given a car and you didn't get a job. So there were no promises broken either way. So this one is true. No promise was broken. Neither side did what they were maybe going to do. And so everything's equal, promise not broken. So let's maybe view this if and only if, this biconditional statement in another way. Again, what it's really saying P implies Q and Q implies P is really what it is. In fact, let's see if that's logically equivalent to that. So let's consider P implies Q and Q implies P. Let's put those two together. And I'll make the table quickly here. You're probably getting pretty used to this. TT, TF, FT, FF. And we said P implies Q, going back to our conditional statement that was here. So it's going to be true, true, false, true, true. And then Q implies P. So again, now this time, this hypothesis, and that's a conclusion. We have to look over here. We have to kind of go the other way. So true, true, that's going to be true. False, true. Remember, if you have a false hypothesis and you have the true conclusion, there's no promises broken here. So that's got to be true. Here, though, if you have a true hypothesis and a false conclusion, a promise was broken. False. And again, if you have a false hypothesis and the conclusion false, no promises are broken. So that's true. So now let's put these two together. And so we want to put these two together here. P implies Q and 2 implies P. So again, remember with the and, these both have to be true for this to be true. This is false. This is false. This is true. So this is very important. Notice that we get the same thing. So this has the same table, the same column as the biconditional. Remember, biconditional had true, false, false, true, true, false, false, true. So this statement is logically equivalent to this. Again, same truth table as the biconditional. So that means that the biconditional statement and the two conditional statements put together are logically equivalent. Which kind of makes sense. That's kind of what if and only if means, that you're kind of going both ways with these. Now we're going to talk about arguments, valid and invalid arguments. First, we're going to need a definition. An argument is a sequence of statements all the arguments, excuse me, all the statements, I should say, in an argument, except the final one, are called the premises. The final statement is called the conclusion. An argument is valid if and only if the conclusion is true whenever the premises are all true. So now to evaluate a valid argument, we just have to check the cases in which the premises are true and verify that the conclusion is true in that case. Again, let's take an example. I think I got this from a textbook by Tan. And so, again, let me put that in parentheses. So the premises Arthur studies hard. Arthur will pass the exam and Arthur studies hard. Now, these are the premises The first one is if Arthur studies hard, he will pass the exam. The second one is Arthur studies hard. Then a lot of times you put like a line here. And then the conclusion is Arthur passes the exam. Again, this is last part is the conclusion. So this argument has two premises and one conclusion. And you could actually sort of state it again. A lot of times I put a line here right after the premises and before the conclusion. Now, if you want to write this in symbolic terms, again, you could maybe call this first one here P implies Q. In fact, let me just write this out maybe a little bit more in detail. Again, usually you're not going to have to do this. We're usually just working with the tables. Let me just kind of give we have here. So let's say a P is Arthur studies hard. Q is Arthur passes the exam. So let's say those are our propositions. Now again, let's put this argument here in symbolic terms. So this one is saying P implies Q. This one is what just, excuse me. Yeah, this one is just Q. This could be just P, isn't it? So this next one is just P. So those are two prepositions, P, Q, P. And our conclusion is Arthur passed the exam, which is Q. And a lot of times we want to put therefore, and these three dots in triangular form, you're probably familiar from math, that means therefore. So these are the premises and conclusion. We usually put therefore right before the conclusion. So here's a statement of the argument. There's the argument. There's the argument in symbolic term. Now let's evaluate. Say, is this a valid argument? So we'll have to put it all on a table and see. Like I said, we just have to check the cases in which both premises are true and see if the conclusion's true. We're going to make our normal table TT, TF, FT, FF, so let's take a look at this here. We're going to need P implies Q. And remember, P implies, this is true. This is false. This is true. This is true. Remember from our conditional statement. And so now here we have our two premises, and then our conclusion. And maybe sometimes, again, you could just work with this right here. And if you really want to get super organized, you could put the premises and the conclusions together. So let me, for this, again, you don't have to do this. You have everything here, but let me just organize this just slightly better. So let me just rewrite P here. T, I'm just rewriting the column P just to have it here. And the column Q, like here. So then again, the only reason I wrote it this way is just so I'd have the premises here. And the conclusion here. And again, remember, we only have to check the case where the premises are true, check the case where all the premises are true, and see if the conclusion is true, and then it's valid. So now, let's see, the premises aren't both true here, not both true here, not both true here. They are both true right here. So this is the only one we have to check. We have to check where all the premises are true and see if the conclusion is true. And the answer is yes. It's true. So therefore, the argument is valid. once again, you didn't have to rearrange it this way. You could have just said, okay, this is a premise, this is a premise, this is a conclusion, mark them here. But I just did this so you could see, just organize a little so you could see real clearly. Check when the premises are true, be sure the conclusion is true. Now, if in this case, if the conclusion had been false here, then it would have been invalid. Or if you had had the case where there's two or three rows with T's, you always have to have a T over here. So let me do another one here real quickly. And let's write this one down. If Bill plays football, he sometimes wears a jersey. Bill sometimes wears a jersey. The conclusion is something again, you put therefore Bill is a football player or plays football. So again, you can maybe make the statement here. You'd say Bill plays football is P. Bill sometimes wears a jersey. Maybe that'll be Q. And so if Bill plays football, he sometimes wears a jersey. Bill sometimes wears a jersey. Therefore, Bill plays football. There's a football player. And this would be, say, a P here. So our argument is something like, goes something like this. P implies Q. Q. Therefore, P. And so let's evaluate this. P, Q. P implies Q. P implies Q is true. So again, this is a promise broken. That's false. This is true, true. And once again, you can just use what you have here, but I'm going to organize it again, put the premises all side by side. Those are the premises there. And I'm going to put the conclusion over here. And not necessary, but sometimes helpful to organize things. So here's a premise. Premise. Conclusion. So we have to check the cases in which the premises are all true. So again, check this case here. The two premises are true. Be sure the conclusion's true. Yes. Here. This one, we don't have to check this. This one we do. The two premises are true. But this time, this is false. So we had to check this one. So this one row here makes the argument invalid. Even though this one up here looked good, this one down here did not. So it has to be true for all the cases where the premises are true, but because here the two premises were true and the conclusion was false, that makes it invalid. And now this one, again, these sometimes have names which we'll possibly get into later. This up here is sometimes called the converse error. And you could often see this, this, you can almost logically look at this and say, okay, if he plays football, he sometimes wears a jersey. Bill sometimes wears a jersey, therefore he's a football player, plays football. You can see the argument is not really logical because if he plays football, he wears a jersey, but doesn't necessarily mean because he wears a jersey that he plays football. That's not what this first statement. These aren't implying that. And then therefore, Bill is a football player. That's not going to be true. So that's an invalid argument to make, and that's called a converse error. And again, there are a lot of other ways to do these. Let me do maybe one that's a little bit more extensive. Walter goes home, he eats lunch. Walter eats lunch. He plays a video game. Therefore, if Walter goes home, he plays a video game. Let's take a look at this. Again, let's call maybe Walter goes home, call that P. He eats lunch, call that Q. We also have a Q down here, then eats lunch. And now we're going to need a third proposition. He plays a video game. You have to call that R. And then finally, the conclusion. Remember, these are the premises. These two are the premises, and this is the conclusion. And so let's see, if Walter goes home, that was P. And he plays a video game, that's what we called R. So the argument looks something like this. So this one is, the first one there is what P implies Q. Q implies R. And then the conclusion, therefore, P implies R. So let's take a look at this with our truth table. And let's go ahead and make that up. And remember, when we make a truth table with three things, we go true, true, true. Then false, 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 false. And again, remember, four truths, four falses, then do the usual true, 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 false, false, true, false, false. Do the same thing down there with these ones. Do true, 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 false, false, true, false, false. There's a few more lines. Hopefully your lines are straighter than mine. So again, let's do our premises. P implies Q. Remember, that's our conditional statement, which is only false when the hypothesis is true and the conclusion is false. So here we're going to have true, true, and then false, false, true, 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 true. And let's go to the next one. Q implies R. True, false, but the hypothesis was true and the conclusion is false. This is going to be true, true, true. This one's false. True, true. Finally, our conclusion is P implies R. And that's going to be true, true, true. Now that one's false because the hypothesis is true. Conclusion is false. True, 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 true. Is that right? Yeah. Let's see, I should have another. I made a mistake here. Please fix this. This is true, false. This one should have been false right here. Please make that false right there. So now let's see. So again, this we have to check all the cases in which the premises are all true and see if the conclusion is true in those cases. Let's go through here. Let's check. Let's see. Here, I'll just mark them to start with. Here, the two premises are true. Here, they're both true. Here, they're both true. Here, they're both true. This time we have several to check, 4 to check actually. So now let's check here whether true is the conclusion true. Yes. Remember, if we get a no for any one of these 4, it's invalid. So here, this is true. How about this row? It's true. We have only one more to go. True. So again, if any one of these would have failed, it'd have been invalid, but the conclusion was true in every case in which the premises were true. So if I could write the word down here, this argument is valid. So this argument, P implies Q, Q implies R, therefore P implies R is a valid argument. Just want to mention a few more things. The contrapositive of P implies Q is not Q implies not P. The converse of P implies Q is Q implies P. And the inverse of P implies Q is not P implies not Q. Now, these two, and you can show this, these two are logically equivalent. The converse is not logically equivalent, and the inverse is not logically equivalent. So let me just write that down. Logically equivalent. These two are not. And this also is not. later on, if you want to, when you want to do proofs, if you want to prove P implies Q, sometimes it's easier to prove that not P implies not Q. Now, these other two are just definitions and they're not logically equivalent. You can't really use this to prove this. You can't use this to prove this. But this one you can. The contrapositive, you can use the logically equivalent form to the contrapositive to prove that. And again, converse and inverse. Again, these are just definitions. They're not logically equivalent.